Dr. Wolfgang Banzhaf is the John Koza Chair for Genetic Programming in the Department of Computer Science and Engineering at Michigan State University. He has authored several influential books, and he is founding editor of the Genetic Programming and Evolvable Machines Journal from Springer. Banzhaf's contributions to the field of genetic programming have earned him numerous accolades, including the ISGE Senior Fellow Award in 2003, the Evo Star Award for Outstanding Contribution to the Field of Evolutionary Computation in Europe in 2007, and the Lifetime Achievement Award from the International Society for Artificial Life in 2022. Thank you for your availability, for being here with us in this interview. You're welcome.
Thank you.
Well, we are here at the Evo Star 2023. This is my third Evo Star, but of course you have much more experience than me.
Yeah.
And what changed in Evo Star during the years? How do you see the evolution of the conference itself?
Yeah, this experience comes with age, necessarily. I'm older, as you can see. Yes, that's true. So I was involved when we first started this entire thing in 1998. And at that time, it was a small workshop on genetic programming that we started, and that was that was one of two events. We had two events at the time. One was this EuroGP workshop, and the other one was a evolutionary robotics workshop. Those were the two events at the time. What has changed over the years? First of all, we became a conference. Then we became a conference that strives to become recognized in the rankings of all the scientific conferences, to be in the best league of the conferences. We introduced awards for people that students and for best papers and so on, and so it became more and more established over the years. That's necessarily clear. In terms of participants, we have always had, from the beginning it's clear that everybody was new to this, but over the years we have tried to be as open as possible so that new people can join us and feel welcome in this community. And I think that hasn't changed since the beginning.
Nice.
We are hopefully still welcoming new people every year to the field and to our own groups and so on. In terms of the constitution of the participants, my feeling is that it has become more diverse over these close to 30 years, 25 years. More diverse, both that we have more female participation now, which is, I see this in particular this year as a good sign, and then also more international and having participants from overseas.
Do you think that this increase in diversity of the participations is due to the increase of the use of evolutionary computation, or it's because the conference itself is growing, or both?
Okay, the conference is not growing. Actually, it might have been shrinking over the years. I don't have the numbers by heart, but I think there was some peak at some point in the 2000s, and we are not at that peak right now with our numbers. So it's not the number. I would guess that it is indeed the field that has sort of percolated in many different directions, including applications, and that people from other universities that may have not had people working in evolutionary computing now have people working in this field, and send someone to the conference.
Nice, so. Interesting. So you're the author of the book Genetic Programming and Introduction from 1997.
Yeah,
right?
right. It was published in 1998, but we are targeted 97. We just couldn't do it in 97.
Well, there is a chapter in this book that is called Advanced Genetic Programming, and it has 3 topics: improving the speed of genetic programming, improving the evolvability of programs, and improving the power of search of genetic programming. After these 26 or 25 years, if you could choose one of these topics to work nowadays, which one you choose and why?
Okay. To be honest, I find them all interesting. I mean, you're giving me the task to select one, and I will select one, but I find them all still very interesting. In the sense that while we have made progress in these 25 years, we are far away from having exploited, from having harvested all that is in these areas, possible in all of these areas. So let me start with the speed. There were various attempts to parallelize genetic programming, and when the GPUs came up on the market after game playing became modern, GPUs were really a success economically, and they were spreading onto all computers. We worked on GPU, genetic programming GPUs. Was a bit difficult, and we haven't really made big improvements in speed, maybe factor 100 or 200, but not the 10,000 or 100,000 that you would like to have from these kinds of cellular processors. So that was a bit of a disappointment. But I still find this interesting field today, more in the sense of, can we use FPGAs? So new hardware that's coming on and spreading in the hardware, computer hardware area. So, and we need speed. We need as much speed as we can use. So that is still an interesting area. Let me just say one thing about this in terms of a quote that I have from Richard Sutton, who is the co-inventor of reinforcement learning. Co-author of the book on reinforcement learning with Andrew Sutton. And he says, he has a blog post that is 10 years old, maybe less than 10 years, which he headlined the bitter truth or something like that. I forgot the exact title, but what it's talking about is that over the 70 years of computing evolution of artificial intelligence and machine learning, researchers have put in a lot of their ideas and ingenuity into improving by adding knowledge, human knowledge, into these systems, and all of this was disappointingly made obsolete by the progress in the computer speed and the hardware speed. Pure raw power, exponentially growing over many decades, has beaten all the human ingenuity that went into, we have to twiddle these algorithms a bit and put in a bit more knowledge about the problem that we want to solve. It was always the raw power over these years, or not always, but it is now visible, clear after this exponential growth. That is the raw power of the hardware that made the difference between solving a problem and not being able to solve a problem, or solving a problem better than worse. And so it's disappointing. The bitter lesson, it was called. It's disappointing for researchers that put in so much of their own energy. They could have just sort of waited a couple of decades. Of course, you live during those decades and you pass away. That it happened like this with just the material raw power of the systems. So in that sense, we still need to have attention on the improvement of the speed, because that is also something that GP can harvest, or continues to harvest in the future. So if you ask me to choose one of those three, I would say evolvability is the most interesting one, evolvability of programs. But I would not dismiss the search either. So all three are still interesting. Evolvability, why would I say this? I think that we have, maybe I contradict myself, because that is in some sense ingenuity that we put into our systems. When we say, okay, we have to twiddle with the representation to make it more evolvable, but I think that this is a key part. And in evolution, in natural biological evolution, evolvability has played a big role over the billions of years of evolution, also because evolvability itself, as it has been found, has evolved. So it has become better and better in biology, and probably we can mimic or we can copy this success story. So in that sense, I find evolvability, if I have to select one of those three.
I see.
Yeah.
Interesting. Yes. Interesting point of view that we have to remember that the evolution itself is also evolving. So
yes,
yeah,
exactly. Now you could argue it is very much related to the search as well. I mean, so it is, these are connected topics.
They are connected, but okay, good point. And how do you see the connection between complexity and evolution?
Oh, that's an interesting one. I have recently become very much interested in that because there are mathematical results from algorithmic information theory. I mean, we are now talking about evolution, artificial evolution, that say that it is actually the simple solutions. If you search with a stochastic search, that is actually the simple solutions that you find to be most abundant in discrete input-output systems, which can be construed to be systems like genotype-phenotype maps. So you start with you take, if you look at arbitrary genotype-phenotype maps, which are input-output maps, and look at the solutions, that is the phenotypes, you'll find that the most frequent phenotypes are the most simple ones. And that is very interesting. We tend to think that evolution actually works in complex spaces and produces complex solutions to problems. And I was of this opinion for the longest time. I was thinking, okay, there's this complexity threshold below which solutions cannot solve. The solutions are not perfect, or they are weak. And above a particular complexity threshold, they become close to real solutions to a problem. And I'm not withdrawing that idea. I think that's clear that this is happening. But then I was thinking, okay, and above that threshold are so many more solutions that are of higher complexity. So it's natural that evolution tries to find, or will find, one of those more complex solutions to a problem, and then gradually maybe come down to a simple solution. But it turns out that because these simple solutions above this threshold are the most abundant ones, evolution tends to hit those solutions first. And that's all it needs. Once it has a solution, it's done. Evolution is lazy. So it's, by the way, also maybe one of the explanations for why we have systems where evolution finds shortcuts. Shortcuts could be considered simple solutions to a problem that, we pose a problem to the system and it takes a shortcut and exploits some oversight in the design of the fitness function or some bug in your code or system in a game or so to get to the best solution that it can find. And but we are disappointed afterwards and surprised by saying, oh, it didn't do what I wanted it to do because we have not defined the problem correctly. But it found this simple way out of the problem that was posed to it, and that's fine. So it seems that simple solutions are actually what evolution prefers, not because it has a motivation for that, but because they are more abundant. They're more abundant.
Okay. So it's easier to get there because they are more abundant.
Yes.
Okay.
Now, you can ask why that is, but that's a different story.
Okay. And the evolutionary computation algorithms have random components.
Yes.
Which make them different from other intelligence, artificial intelligence algorithms, right? We have this particularity. And from your point of view and from your experience, why would this be an advantage?
Okay. I think it has to do with creativity. If you have randomness, I have a couple of points about this. One is if you have randomness, you cannot predict exactly what's going to happen because that's the very essence of randomness. It's not predictable, and therefore I think that we have a chance to find solutions to problems that were not foreseen, that were not sort of expected. And that's I think a good thing because for many problems in our world we need solutions where we have no idea how to get to them. I think that's also a reason why these evolutionary algorithms are damn fast to find solutions where we don't have analytical ideas how to solve them, because they are not maybe perfect, but they are at least fast to get to a point where maybe acceptable solutions can be found. So that's I think one of the strengths of non-deterministic stochastic algorithms. And the other one, I would say, has to do with the fact that we are forced by this stochasticity to use populations. We have to sort of look at large numbers of these individuals that try to solve a problem in order to get to a good solution. Because of the stochasticity, we cannot afford to do that with one individual normally. So populations are an answer, however, also to the problem of our world that has an unpredictable environment. So what better way to respond to an unpredictable environment than with a population? Because a population with diverse attempts to solve the problem, the adaptation to the environment is sort of a more resilient possibility of solutions than just having one, maybe a gradient optimal to one particular environmental condition. But if it's changing, then we are lost, probably with a single solution. But with a population that we are forced to use because of the stochasticity, we have much more resilience in those, in the entirety of the population. You can say, well, this is wasteful. Yes, it is wasteful. It requires a lot of computation time, a lot of storage space, and so on. But I think this resilience or robustness or so is
worthwhile.
Yes, it's worthwhile.
Nice. And besides the complexity and evolution connection, which are your other main interests currently in evolutionary computing?
GP? Yes. So, I talked about quite a few things already. So we also do applications, but applications are something where I'm happy to collaborate with colleagues and so on, but applications have this taste for me of not being fascinating. Okay, most of them. Yes, for a bit of time, but not really driving me.
Because our applications are the algorithms itself.
Yes, exactly, yes. So we are, I think many in our community are are fascinated by how evolutionary algorithms work, and they want to understand what's behind that mechanism of working. And you sometimes sit in front of your computer, you watch it evolving, and you ask, why, how did it happen that this stochastic algorithm finds such a good solution to, let's say, in my case, finding a bug repair patch or something like that. So this is just really fascinating in itself.
Okay, nice.
Yeah.
And you are in a sabbatical period now, but I saw that you have a course on multidisciplinary approaches to the study of evolution. It seems a really interesting course, and also a great opportunity for people with different backgrounds to learn, to interact, and to be there together. And it's very interesting. I think that for us, specifically who works with nature-inspired algorithms, it also can be a very fruitful experience.
Yes.
So could you tell more about this course and this multidisciplinary experience?
Yes, sure. I can try to explain what we do. Now, I have to say, this was not my invention, my initiative. This was already existing at Michigan State University, where I now teach, before I came. And my colleagues who developed that course have graciously agreed that I can also teach that course. And we are teaching it always as team of two. And so one is from one department and the other is from another department. So computer science, I'm currently the one that teaches it. So it's always a mix of people that does this. And that's also what we strive for in the student population for the course. So it had a different name to it. It was called the Beacon course. That is, Beacon is our institute for research in evolution. It's called the Beacon Institute for the Study of Evolution in Action. That's our title of the center, and Beacon Center, I should say. And so people in that center have developed that course, and I'm happy to be part of it now. Now, for the students, the main point really is that they have to learn to communicate with each other, because that's the idea, they come from different disciplines, and it's a project-based course, so they have to work together. We try to put teams together where people come from different disciplines. So let's say a biologist and a computer scientist, or an engineer and a computer scientist, or a theoretician and a practitioner of some disciplines. And so what this requires is that they will learn among themselves, collaborating, to listen to the aspects of a field or a problem from the other perspective, because the other student will hopefully bring that other perspective in, and it requires time and requires patience to understand, sometimes adaptation of one's own language, because it can be tricky. You use the same words, but you use them for different things. So interdisciplinary or cross-disciplinary work is always challenging, and in this case, students learn it in this course team project to suffer through such a thing, right? And the success depends really on the ability to understand each other and work together in a team of coming from different disciplines. Also, because the faculty that's teaching is from different disciplines, that brings in different aspects into the lectures. We give a few lectures in that course, but the main emphasis is on the team project. So about 10 lectures maybe, and the rest is interspersed, is finding a project, defining a project, and then moving on from actually aspiring to something to actually achieving something, which can be challenging and sometimes ends up very successful and sometimes not so successful. Both of these are learning experiences.
When communication doesn't work, it's not successful.
Yes, exactly.
But otherwise, I can imagine that it's like a synergic process, because then we have these 2 points of view that are different and that can interact and learn with other and
complement each other. And for example, when biologists and computer science, sometimes the person that is educated in biology would say, "Oh, I can't do the coding. You do the coding," but they have to work together because the problem description and so on, that has to be maybe coming even from the biologists. We want to have all parties involved to have at least the opportunity to make a contribution.
Nice, interesting. And would you like to give some advice for young scientists in the evolutionary computation field?
Yes, I think science is a social enterprise. We should be clearly aware of that. Science is a social enterprise, which means that there are certain like in flocks of birds and other, there are certain behaviors or certain topics that are of interest to everybody, and they are sort of en vogue, or what was the current fad, and tomorrow it's something else. And so scientists sometimes, I have the feeling scientists are very often very conservative in the sense that they go for what's the safest thing that everybody also says, oh, this is a good idea, and so on. But I think science progresses by the outliers, that is, by the people that search in corners of the problem space where other people don't search. I mean, we know that from our searches, that we need both exploration and exploitation. So not everybody is an explorer. Some are maybe more the second front, not the pioneers, the second front that sort of clean up all the bad ideas or errors from others. So there's a different characteristics for people, and some are better at this role and others in another role. But I would say it is important and also inconvenient to be, let's say, trying to do something new that others have not, or asking questions that nobody has an answer to. It's inconvenient. It's not what most do, but it is a really important activity in fields. And I would encourage the student population of the world in evolution computing to be courageous and do things that nobody has tried. And I think for me, that's the exciting part of research, not just doing a little variant of something that someone else has done already for a long time, and it's just a bit of a little tweak to that thing. Yes, you can build your career on little tweaks or on making things more complex by mixing it with other approaches. All of that is a legitimate possibility for a career, but I think that the courageous explorers are the ones that push the boundaries more, and it can be painful and dangerous for a career, of course, but that's what comes with exploration. So I would encourage people to at least make an attempt to look at problems that maybe others have not looked at, and not just run with the crowd, but try to do something.
Yeah, to do not accommodate in the safe part.
Yes.
Okay, we need to do the safe part, but also keep in mind that we need to push forward.
And it's so easy to get stuck with the safe part. It's more convenient for us as humans to do that, and so we have a natural attraction to that. To that tendency, and therefore it requires more energy to do the other thing.
Okay, thank you so much. And thank you for the interview as well.
Yes,
it was a pleasure.
Okay.
Thank you.
Very good.